someone apologize in there. It is now on. All right. So if you have virtual machines, so instead of having like a lightly used machine, just make them all virtual machines and then run them on a single machine if you want. So to clarify this, so for instance, if you were making a fun web application and you don't want to give yourself a headache later on, well, you could make a virtual machine for like your database, make a virtual machine for your front end, make a virtual machine for your back end, and then when you don't have much traffic at all, you can save a bit of money, run all those virtual machines on the same physical machine, and then once you see that that's overloaded, well, you don't have that much work to do. You go out, you buy another machine, and then you move one of the virtual machines over to it, and you can do that no problem. And if you run out of more, you just go buy another server. Maybe you have more instances of the database virtual machine. Maybe you need more of the other. It makes it real easy to scale and recover and run stuff. Yep.
So is there any way, like, decrease the volume on the speaker from your mic? It's like just off by like,
Oh.
like a couple hundredths of a second. It's like really still.
Okay. All right. That better? No? All right. There. Ish? Hello, 1, 2, 3, 4. Yeah. All right, that better? All right. All right, I will try and be louder. All right. So where were we? Yeah, so if you do something like that, it's a lot easier to move things around and manage them. So like we had a process control block when we were scheduling processes, virtual machines have something called a virtual CPU, and that keeps track of everything about a CPU, including all of the kernel mode only registers and all of the entire state of the CPU instead of just whatever a user can actually have access to. So for processes, it's a process control block. For virtual machine, it's a virtual CPU. So whenever that guest isn't running, the hypervisor is going to save the state of the CPU, and that's what's involved in doing an actual context switch. And if you want, you can resume that virtual machine, just like the process control block, just loads the data from it and resumes. As you might imagine, well, it would have to do a lot more work than just a process control block to actually resume. So context switches are more expensive, but it is possible to do. And you can also context switch across machines if you really want. So the guest still uses user mode and kernel mode. There's no changes at all in the guest operating systems. So the Linux kernel still uses kernel mode instructions. It doesn't change. So remember on x86, if we remember all the way back from the beginning, user mode was in something called ring 3. Kernel mode was in something called ring 0. And well, x86 CPUs were like designed in the 70s or the 60s or something like that. So virtual machines are a new concept. So they were like 20 years ago or something like that. So they needed a new CPU privilege mode that was more privileged than kernel mode. So they called it ring -1 because they ran out of numbers. So on x86, hypervisor mode that you need for type 1 hypervisors is ring -1, so it's even more privileged than kernel mode, and it lets you control all the guests. For type 2 hypervisors, well, the host has to essentially fake kernel mode because it's only running in user mode. So if we were trying to simulate kernel mode in a user mode process, one strategy we could do is something called trap and emulate. So if we try to execute a privileged instruction, so like if you somehow figured out, or you looked at the spec and figured out the assembly for, I don't know, like switching the root page table or something like that, and you try and execute it in your process, well, you're going to get a signal and it's going to say, oh, illegal instruction, you're not allowed to execute that, and that's part of the hardware protection. So if you wanted to, by default, you would get a signal, your process would exit and it would die. But if you were to implement a hypervisor, you could write a signal handler and you could simulate whatever that instruction was supposed to do. So you are going to have to simulate everything that happens in kernel mode on that particular CPU, but you can technically do it. So in your signal handler, you would figure out, oh, what instruction did they try and do? Okay, I'm simulating all the page tables and all the MMU and everything like that. So I'll just simulate whatever this instruction was supposed to do. And as you can imagine, well, it will be slow. So instead of executing the instruction directly, well, a signal gets sent, and then I have to see what the instruction was, and then I have to simulate whatever it was doing. So technically possible, but it's going to be much, much, much slower. And also, this would work if you had a sanely designed instruction set architecture, which x86 is not an example of. So, oh, before that, here's that visually. So, your guest operating system is going to be running in user mode, and it thinks it is in kernel mode. If it tries to execute an instruction that is only present in kernel mode, generates a trap or a signal, and then you would handle it, emulate what it's supposed to happen, update that virtual CPU that keeps track of literally the entire state of the CPU, including all the kernel mode stuff, and then you return and just keep on executing until this happens again. So, trap and emulate doesn't always work. So on some CPUs, well, there's not a clear boundary between privileged instructions and non-privileged instructions. So on x86, virtual machines didn't exist in the 70s. So what they did is they tried to be clever and had some instructions that just had the same machine code, but did different things depending on what mode you were actually currently in. So for instance, there's one instruction called the pop-F instruction, and it loads a flags register from the stack, and that flags register is different depending on if the CPU is currently running in kernel mode or running in user mode. So if it's running in user mode, that flags register is a user flags register. If it's in kernel mode, it's a kernel-only flags register. So the same instruction behaves differently. So if my type 2 hypervisor, which is only running in user mode, while tries to execute an instruction that thinks it is in kernel mode, but just behaves differently, well, it would just execute in this scenario and just do the wrong thing. So I have to be able to fix something like that. So since it doesn't generate a trap and it just kind of executes and does the wrong thing, I call these special instructions, and we have to have another approach for them. So for special instructions, we need to do something called binary translation. So that guest virtual CPU is in user mode. It can keep track of what state it is currently in. So if the virtual CPU is currently in user mode and that guest thinks it is in user mode, it doesn't need to do anything. It just runs the instructions because they both agree with each other. But in the case that the virtual machine thinks it is running in kernel mode, then I actually need to essentially translate these instructions. So all it does is inspect all the instructions before they execute and check if it's one of these special instructions. If it's one of these special instructions, then instead it would execute the simulation instead of the normal instruction. So you can imagine this would also be slow. And how it can do this is, well, it knows whether or not that guest virtual machine knows it's in kernel mode or user mode because, well, there's a CPU instruction that switches from user mode to kernel mode. Hypervisor can handle that using trap and emulate, so it knows what mode that the virtual machine actually thinks it's in. So because of this, it has to inspect all the instructions. Performance is going to suffer really bad, but in general, it kind of works if you have an overpowered machine, and it's more or less adequate. That's what I was going to say about that. Compile your program or anything like that. It will essentially read the instructions your program's about to execute, and if it's about to execute a malloc or a free or something like that, it will go ahead and instrument it and then keep track of your mallocs and frees and that is how Valgrind works, and also why, if you check its performance, it's like 10 times slower or like 100 times slower than just executing your program, because it's doing this. So how that would look visually is, well, my virtual machine, it's only running in user mode, but my hypervisor, also running in user mode, would know that, hey, this virtual machine thinks it's in kernel mode. It would start inspecting all the instructions before they actually get to execute. If it's a special instruction, well, it just simulates or emulates what it's supposed to do, updates the virtual CPU, and then just keeps on executing more instructions. So this is slow, and we don't want to do that, and that's where we came up with that hypervisor mode and have more actual hardware. So 2005, which I guess is slightly newer than some of you, that's when they first standardized virtualization, hardware virtualization. So it was standardized as VT-X for Intel, and then AMD standardized it later as AMD-V. And throughout all your BIOSes, if you need to enable virtualization for some other reason, it might be called different things because they also came up with 2 different names for it. So Intel also named it codename Vanderpool when they were developing it, and then they ratified it as VMX. AMD, their codename was Pacifica. Then they published it as Secure Virtual Machine. But these all 6 of those terms mean the exact same thing. So if you need to enable it in your BIOS for whatever reason, if your virtual machine was slow, I don't think any of you had to do that. And did any of you have to do this? So if you had to do this, or if you want to turn it off for some reason, it'll be called one of those things. They all mean the same thing. So those all add the concept of ring negative 1 or hypervisor mode. And how Windows actually works, like for you with your virtual machine, well, Windows will see that this CPU has hardware support, and when it boots up, it will claim the hypervisor. So it will act as a hypervisor and then normal Windows kernel things. So it will run your applications, your normal applications, as if it was a kernel, and also context switch that out with virtual machines because it's also a hypervisor. So this also, lets Windows set all of the isolation for all the guests and what hardware it can virtualize. All right, so to tie this with other stuff we learned, yes, a hypervisor would have to schedule as well. So if there's only one CPU on your physical machine, well, the guest doesn't know about that. So you could just say, hey, virtual machine, you have 8 processors and you only physically get 1. And then your hypervisor gets to schedule that and do all that context switching and all of that fun stuff. But, well, the trade-offs are a little bit different here because context switching is way more expensive than just context switching between processes. So what you might want to do is just map virtual CPUs on the virtual machines to physical CPUs, or you could schedule them like processes if you want. In general, it's easier just to map them and just keep them on the same CPU so you don't have to context switch them out. But you might choose to just context switch them out like normal processes. So in the hypervisor, it will have hypervisor threads that will deal with all the scheduling and all of that fun stuff. So one approach to scheduling these are, like I said, CPU assignment. So if there's more physical cores on your machine than all of the virtual CPUs across all the virtual machines, just map them 1-to-1. Host can continue using spare physical cores to do hypervisor things if it wants. And if you have to share, that's where things get complicated. That even has a special term for virtual machines, and it's called overcommitting. Overcommitting just means my virtual machines are using more hardware than I actually physically have on my machine. So if I don't overcommit, it's a lot easier. I just kind of map things, and I don't have to worry about context switching. But if I overcommit, then I have to worry about context switching, and things get more complicated. So then you would have scheduling algorithms. They would look exactly like what we use for processes. Sometimes overcommitting also causes additional problems. So for instance, if I was just running directly on hardware and I had a soft real-time task that had some type of deadline, and in practice I met it all the time, and then, well, suddenly I move it to a virtual machine and then I miss my deadlines and bad things happen, well, that's because ultimately you lost control over the hardware if you're running a virtual machine. So in the middle of doing a soft real-time task, well, the hypervisor could context switch out that virtual machine, stop it from executing, and then it would miss its deadline, and then it could context switch back in, and then it says, oh, I missed my deadline, that shouldn't have happened, and the virtual machine has no control over that. So for some things, once you get into like super predictable and things you want to be super high performance, then sometimes running a virtual machine is not an appropriate thing unless you do the mapping and have direct access to the hardware without having to context switch it out. So this is only in certain situations that virtualization causes differences that is not very good. All right, so like we talked about scheduling with virtual machines, well, they also have memory management, except it's even slightly more confusing. So your kernel, that has access to physical memory, and then each process has virtual memory that thinks it can access everything. Well, guess what? Once we add a hypervisor into the mix, the hypervisor has control over physical memory, and then each virtual machine has virtual memory. And then each virtual machine, well, it thinks that virtual memory is physical memory, and then each process has virtual memory, but in reality, that's like virtual memory because it's through 2 layers, right? So it's 2 layers, and each layer would have 3 levels of page tables. That's fun, right? So that's also part of the problem that the hypervisor solves. It lets you have something called, wait, is it on this slide? Yeah, it lets you have something called nested page tables, and that will essentially take that into account with the TLB to make sure everything is nice and fast so you don't have 2 translations going on that aren't aware of each other. So this makes both translations aware of each other, makes sure the TLB doesn't get screwed up, and does all the page table management for the virtual machines kind of for you. So the hypervisor maintains that nested page table, and then the guest would maintain their page table, but it's nested by the hypervisor, and then it would use that to translate for the guests, and there would be hardware support for that. As you might imagine, as soon as you get into swapping, this becomes even worse. So the hypervisor could swap out if it runs out of memory, swap out to disk, but the virtual machine might also swap out to a virtualized disk. So if you run out of memory, you might not actually know which one is doing the swapping. It could be the hypervisor, it could be the kernel that you're actually running, and the hypervisor would have its own page replacement algorithm, but typically the guests or the kernel running knows the memory access patterns better, and that's probably what should actually be doing the swapping. All right, similar to copy on write, there are optimizations in virtual machines to share memory. So just like with processes, I can share memory if the contents of the page are exactly the same and I am only reading it. So unlike virtual machines, there is no fork, and kind of sets you up and lets you know what pages are going to be shared. So what the hypervisor will do is essentially scan all of the pages, take a hash of the page, because that is much quicker than actually comparing every single page byte for byte. So it'll take a hash of the page and then check if 2 pages have the same hash. If 2 pages have the same hash, it means their contents could be the same or they could not be the same, but they're definitely not completely, they might be different, but they don't have to be. So if the 2 hashes are the same, well, then it will do the expensive check, see if they're the same byte for byte. If they're the same byte for byte, then it will start sharing that between the 2 virtual machines. And then, well, if one of the virtual machines needs to write the page, then our same copy on write things are going to happen, where we have to make a copy of that page and then modify it in the new one, make sure they're completely isolated. But the same concept of copy on write does apply for virtual machines, just how you share a page is a bit different. All right, other fun things. So the hypervisor also provides virtualized I/O devices. So you can multiplex like each virtual machine's, say, network card to one physical network card. And the hypervisor could also just emulate devices that don't physically exist. So some weird network card or some, I don't know what else you could emulate, some weird sound card or something like that. So you could emulate that and it doesn't actually exist. Other things the hypervisor could do is just map one physical device to one virtual device in one VM, give the VM exclusive access to that device, but the hypervisor is still in the picture, it's still doing some translation, it's just not doing that much. So there is a hardware solution to speed that up that removes the hypervisor from the equation, and it is something called IOMMU. And that's a new hardware feature now, and what that will do is directly map hardware to a virtual machine. So that virtual machine directly has access to the hardware, and the hypervisor does not get in the way at all. And this is generally used for things like GPUs that don't virtualize very well and don't like being shared. So with IOMMU, you just give a virtual machine direct access to that hardware, and then it can run it at native speed. So there's nothing in between it, there's nothing getting in the way, directly uses that GPU. And then, if you were running Linux, you could create a Windows VM, map a graphics card directly to it, and then suddenly you have the same performance as Windows as you would have if you just ran it directly on the hardware, because the most important part isn't being virtualized, nothing's happening to it, just goes directly to the virtual machine. So this is what GPU instances will have. They'll just directly map a GPU to a virtual machine. All right. So virtual machines also boot from a virtualized disk. So you create a disk image, and that has all the contents of a physical disk. It just looks like one big file. So it would contain partitions, and then each partition has a file system, and that file system would look exactly like what you're doing right now in Lab 6. So in Lab 6, if you knew the contents of the kernel files and where they should be and all that fun stuff, well, you could set it up so you could actually boot a virtual machine off your disk image and actually start running a virtual machine. Because usually it's like what you're doing in Lab 6, it's just one big file. Some formats allow you to split it up into little pieces, but the guest kernel just sees it as a normal disk that it has full control over. It can read and write and access it, and it just looks like a disk to it. So this disk image is all you actually need for a virtual machine and makes it easy to move. So for instance, if your computer died and you saved an image of your virtual machine, well, all you have to do is copy your virtual machine image over to the new computer, and you can just boot it up from that, and it will look exactly the same as where you left off. So it makes it really easy to move, and if you use some virtual machine software like VirtualBox, sometimes they'll fool you into thinking a virtual machine is this really complicated thing that needs a lot of things, and they even have their own file extension for it called OVA. But really all that is like a configuration file that says like how much memory and how many CPUs and what network card this virtual machine should have. And 99% of it, aside from that configuration, is all that disk image, and that's it. So they just package it up so it will import the settings from you, but really the disk image is the only thing that's actually important. Just like for your physical machine, the disk is the only thing that's actually really important. You could tear out your disk, move it into a computer, and it would work. So another nice thing you could use virtual machines for is to isolate an application. So remember with dynamic libraries, if we had an ABI change, bad things happen. Like we could suddenly change, sometimes you could even like change libraries' behavior, break applications. So generally when you deploy applications in the real world, you kind of freeze all your dependencies together and deploy them together. But instead of managing, like for this application, I need version 1.2 of this library, and for this application, I need version 1.3, and then installing them both on the same system, making sure they use the right one is a pain. Generally, what you do that's a lot easier is just create a virtual machine for it that just has the library you need, and then you give someone the virtual machine and say, hey, run this, it has everything you need, don't worry about it. But the drawback to that is, well, my application might be a few megabytes, and I also have to supply a kernel with it. If it's a virtual machine, that might be a gigabyte, so that's wasting a lot of space. So there's a solution to that. Has anyone ever heard of Docker? That's the solution. So containers like Docker, it aims to have all the same benefits of virtual machines, except just faster, and you don't have to give it a kernel. So remember the hypervisor lets you set limits on CPU time, memory, network bandwidth, all that fun stuff. So some kernels, well, not some kernels, only one kernel, the Linux kernel, lets you have all those features just without virtualization. So on Linux, there's something called control groups or C groups that support these hypervisor-like features, like isolating processes to something called a namespace. And then you can set what that namespace has access to, like mount points or files, IPC, things like that. And it runs as a normal user process, but it is isolated from the other processes that are running. So containers, their goal is to give you all the same benefits as a virtual machine, except that, well, they just all reuse the same kernel. So if you're using Docker on Windows or Mac, guess what? You're using a Linux virtual machine, and then Docker is running in that Linux virtual machine. And it's all your Docker containers are using that Linux kernel that's running in that virtual machine. And they're all sharing it. But if you're running on Linux, it would just be using your kernel directly, which is why Linux is the good operating system. So everyone uses Docker, guess what? You're using Linux. All right, any questions about that? Alrighty, so virtual machines, they virtualize a physical machine. So they allow multiple operating systems to share the same hardware. They're isolated from each other, so the hypervisor is the one that actually controls all the resources. A type 2 hypervisor is going to be slower because it's running all in user mode. It's like trap and emulate and binary translation in order to simulate kernel mode. Type 1 hypervisors are supported by hardware, so the kernel is actually still running in kernel mode, just there is another privilege mode that is even higher privilege than kernel mode called hypervisor mode. And there's also other techniques to speed things up, so like IOMMU to give a virtual machine direct access to hardware and exclusive access. Then we saw hypervisors could overcommit on resources, but they're nice because we can physically move virtual machines around. And containers basically aim to have all the benefits of virtual machines without the overhead of providing a kernel all the time. They all share the same kernel. So with that, just remember, pulling for you, we're all in this together.